Alright, LAB3, massive black hole. Let's get into it. So, a little bit about the introduction about the lab and how it relates to the momentum principle. So basically, we were asked to find the mass of a black hole, and in order to do that, we had to analyze the star's motion to find the net force for the star. And using this net force, then we could use the gravitational equation in order to find the mass of the black hole. So, as we knew from this lab, the only force acting on the star was the force from the black hole, right? And so the net force is equal to the change in momentum. So therefore, we can use the momentum principle, which has two components, the parallel and the perpendicular components, to calculate the force parallel and the perpendicular and add them together and gain the net force in order to solve for our mass of our black hole. So basically, as we already know, the perpendicular component will always face towards the center of the kissing circle, and this involves rotation. And the parallel component will always face, same as velocity, parallel to the force, and what's it called? This is speeding and slowing down, as we will see in the models coming up. So in order to find this motion, because obviously, we can't track the motion of a star, we did it synthetically through a code. So as you can see, we have the initial conditions here. So the given mass of the star and the delta t, which was a day, and we just converted that to seconds. And so as you can see, we have a while loop, and we calculate our velocity initial and our velocity final, which allows us to calculate then the momentum, since it's just those velocities multiplied by the mass. And then we can calculate our delta p just by taking the final minus the initial momentums. And then dp dt will of course just be that delta p divided by the delta t. And our net force overall will be dp dt. And as you can see, then we can calculate p hat in order to calculate the parallel momentum as well as the perpendicular momentum. And the net force overall will be the sum of both of these. So that past code was all for finding out the net force. And we need the net force because we know that the net force is equal to g times the mass of the star times the mass of the black hole divided by the radius squared, right? And so we're given the radius squared, and we just found the net force, and we have the mass of the star. So we can rearrange the equation to equal that thing that you see on the screen. And then we can input that into our closed script code, as you can see there, the MofBH, and then we can find what the mass of the black hole is. And as you can see above, we actually have an arrow scale that will give us some arrows so that we can visualize how the forces just look through the course of the trajectory of the star. So I'll show that on the next slide. Alright, so here are the computational model results that we got from the closed script code. Let's skip down to the net force real quick. So as you can see, that's the value of the net force we got, and the parallel and perpendicular components respectively. So let's take a look at the arrows now so we can visualize what this looks like. As you can see, the orange arrow will visualize the F-net vector, so the total net force. This will always point towards the black hole, obviously, because that's the only force acting on it. So then we have the cyan vector, and this will always point towards the center of the kissing circle, and the parallel vector will always point just parallel in the direction of the motion. So this is speeding up and slowing down. So as you can see, when it's moving towards the black hole, it is speeding up, and when it's moving away, the arrow is just pointing to the left, so it's slowing down. And the arrows are different magnitudes, which shows like the law of gravitation, that objects that are closer will have a higher attraction than objects that are a further distance apart. All right, so let's answer these concluding questions. So first off, how does the perpendicular and parallel components of the net force differ from the rate of change of the momentum? So basically, you can think of it this way. Even though they have the same direction, the net force causes the momentum to change. So if you think about it, the net force can act as a cause while the dp/dt acts more of an effect. Now, what if the black hole was removed and a different black hole was placed in the same location? and the motion remains unchanged. Now, can you tell what the mass of the black hole is? Well, if I think about it, I said that, yeah, if it's the same trajectory, then that means that it has to be the same velocity and therefore the same momentum. And since the only force causing that is the gravity from the black hole, then the mass would have to be the exact same. However, if they were different, then the mass would not be the same, but you could still calculate the mass of the black hole just like we did in this experiment. So that was my lab, and thank you for listening.